Okay, so good afternoon, everyone. It's a great pleasure to have Frederik here with us today. He is a computational astrophysicist at the Institute of Astronomy, KU, Leuven, Belgium, where he develops simulations to model the atmosphere of evolved stars. Welcome, Frederik. You can start the presentation now.
Thank you very much. So, yeah, indeed, I was a FWO fellow at the Institute of Astronomy, but currently I'm a research scientist at the Leuven Gravity Institute. But indeed, most of the things I will talk about today are things I developed at the Institute of Astronomy, and I'm still collaborating with them. So, cool. So today I'd like to talk about data-driven surrogate modeling for astrophysical simulations. So this is work I certainly haven't done alone. I had the pleasure to collaborate with all these wonderful people you see listed here below. And in particular, I'd like to point out Silke Maas, who defended her PhD last week, actually, and who did a lot of the hard work that I will present today. So shout out to her. Then, okay, so the two papers, the work I will present today is actually summarized in the following two papers. So one is by Silke. It's about machine learning approach to chemistry emulation, and the other is about Bayesian inverse modeling of spectral line observations. So both are already on arXiv. So if you want to look them up, you can find them there. They should also be published soon in the Astrophysical Journal, but they're currently going through. Well, the first one is already reviewed and is in press. The second one is still under review. But I guess before I dive into the meat of this talk, I should probably first give you a bit of context, because I can imagine that not every one of you is working with astronomy or astrophysics on a daily basis. So let me first introduce to you what it is that we care about and what the kind of problems are that we are trying to solve. So here in Leuven, astrophysics is much focused, or mainly focused on stellar astrophysics. So we study things from stellar winds to supernovae. So that's everything that has to do with stellar evolution. I'll try to walk you through the what, why, and how of stellar evolution and what we try to do here. So first, what is stellar evolution? So first you need to know that, stars evolve. So they are born and they die. They haven't always been there and they won't always be there. So they are born when these large molecular clouds collapse under their own gravitational weight, and they form these denser regions that then collapse and start burning hydrogen into helium and then start all these nuclear fusion reactions. One important thing to note about that is that these stars very often are not born alone. So they often grow in pairs, triplets, or even quadruples, which is something that we kind of always realize, but only quite recently are we really realizing how important this is for the evolution of the life of a star. And a lot of all the current research in stellar evolution is about trying to figure out how all our evolution models, which usually just assume a single star, have to be adapted to this multiple star paradigm. So how this works with binary systems or triple systems. So also some of the work I will present today is actually about exactly that, how to move to higher order systems there. Okay, so these clouds collapse into these nuclei that we then eventually call stars if they ignite. Another thing you need to know is that at the end of their lives, these dying stars will lose mass in these kind of outward directed stellar winds, as we call them. So there's winds of material departing from the surfaces of these stars. And by doing so, they will enrich the universe with all their chemicals. So these stellar winds are actually quite unique in the sense that most of the universe is quite empty and hostile to chemistry. But in these stellar winds, you have kind of right about the right density, and you're shielded enough from radiation that actually a lot of interesting chemistry can happen there. So it's interesting to see how chemistry comes about there. And then finally, I also should mention that for massive stars, so everything I told you so far is usually for low to intermediate mass stars. For massive stars that have masses above 8 times the mass of our own sun, they can undergo core collapse, which basically mean that they collapse under their own gravitational weight and then produce these supernovae, which is it's also a mass loss process, but much more violent than these stellar winds. Because it is such a violent process and difficult to model, I will in this talk mostly focus on the lower mass stars and these nice stellar winds, because they give you nice images and they're slightly easier to work with, and give these nice examples that I can show you later on. Cool. So, but why are we interested in stellar evolution? First of all, because of the chemical history. So here you can see a periodic system where you can see where all these elements actually originate from. And as you can see in green, you have these asymptotic giant branch stars. So these are these lower mass stars in their evolved stages as they lose their mass. And in blue, you have the core collapse supernovae. And you can see like a lot of these elements, if you look at how their abundance evolves, a lot of that comes from these asymptotic giant branch stars and these core collapse supernovae. So if you want to understand the chemical history of a universe, we need to understand how these stars and these supernovae actually happen and how that works. And if you can understand the history, it means we also can understand the future, because all these elements will form the building blocks for the next generation of stars, planets, and perhaps also even life. But to be fairly honest, so these are all the more scientific motivations for this work. But for me personally, I just find astrophysics a very nice playground of problems where I can apply all my beautiful math, data science, and engineering. And I guess also for you, this might be more of a motivation to be interested in astrophysics. So how do we then do this? Because we have a clear goal. We want to understand these stellar winds and these supernovae, but how can we do that? On the one hand, we have observations of these objects. So what you see here is an example of such a stellar wind. So the star is called R Aquilae, but actually the star, you don't really see it in the image. It's like hidden in the central pixel here of the image. What you see here is actually the outflow. So this is the stellar wind. And in particular, you see here the CO, so the carbon monoxide that is flowing away from the surface of this star. Now, how do we get these observations? That's actually a nice mathematical story. I won't go into all of the details of it. If you're interested, I can give a whole talk on that. And we also have an interesting project on this. But just to get you an idea of how involved the idea, the whole process of finding these images. This is an interferometric image, which means that we measure the electromagnetic field at different points from a certain patch of the sky. And what we then do is we need to correlate this electromagnetic radiation. By doing that at different baselines, so for different separations of these detectors, we can then get an idea of the Fourier transform of the actual image, the actual intensity that we see in the sky. So then after doing a Fourier transform of these correlations of the electromagnetic radiation that we have, we can actually get these images. So there's a whole bunch of interesting engineering and data science behind this. But for this talk, we can just assume, I think, that we have nice images that we can look at, and we can look at these objects also in different frequency bands. That's also something that will be important later on. Cool. So on the one hand, we have these observations, but on the other hand, we also have simulations where we try to recreate the things that we observe, and we try to understand which processes actually give rise to all the structures that we see. Here on the right-hand side, you can see an example of such a simulation. So in the center, there is a mass-losing star. Initially, this mass loss happens in a spherically symmetric way, but then there is a companion, so a second star or a heavy planet, if you want, that is actually stirring up this a priori spherically symmetric outflow, and thus creating all these complex structures. And it turns out that by studying these structures, you can actually figure out a lot of the properties of this initial system of two stars. If you're interested in that, so that's all explained in these papers by my collaborators. But what goes into these simulations? So there's a bunch of ingredients. First of all, there is the hydrodynamics that describes the flow of material in these models. Then there's also the radiation transport. So that's the transport, in this case, of electromagnetic radiation. That's important because we believe that the actual pressure, the thing that pushes out these stellar winds, is actually the radiation pressure from the star in the center. So if you want to model these outflows, you really need to have this radiation field in there. And also, of course, what we see is the electromagnetic radiation. So if you want to know how these things appear in our observations, you also need to know how the radiation transport happens throughout these objects. And then finally, there is also a whole bunch of microphysics and microchemistry going on in each individual cell in these simulations. So for instance, we need to know the quantum statistical state, because that will determine how these things actually interact with light. And also we need to know the chemical kinetics, because if we're interested in what chemical output we will get from these models, we need to trace the chemistry throughout these models. But it will turn out that doing the chemistry in these models is actually computationally a very demanding process. And that's where the surrogate modeling will come in later in this talk. But first, I want to point you to another problem that I want to talk about in this talk. And this, when you put together our observations and our simulations. Now, ideally, you would want to compare the two. And as you can see, okay, yeah, at first sight, they might look quite similar, but they're not exactly the same. So it's very difficult to constrain your simulations or the models and all the theories that we have to constrain all of that directly from our observations, simply because, yeah, it's these hydrodynamics models are very chaotic in nature, and it's very difficult to figure out which initial conditions will actually give rise to which kind of structures. So yeah, it's very difficult to solve this inverse problem. So that's why we also are working on the inverse problem, where we actually try to directly model observation and capture observations directly into models. Now I see there is a question, or there is something in the chat. Okay, that's not, okay, I don't have to care about that thing in the chat, so I'll just close that window and continue. Cool, okay, so the two things I want to talk about are first is chemical kinetics, and second, this method of reconstructing models based on observations. But let's start with the chemical kinetics. So the chemical kinetics is all about how much of a particular atom or molecule is there present at a certain point in our simulation. How this is usually described from chemistry or from what we measure in the lab is that we can describe this process by a set of coupled nonlinear ODEs. So I tried to give a general description here. And these ODEs, they give, so N is the abundance of a particular species, and I is the index of the chemical species. So I is 0, for instance, corresponds to hydrogen. I is 1 is then oxygen, and so forth and so on. And then on the right-hand side, there are two types of reactions. You have the production reactions that tell you how much of this chemical species is created, and then the destruction reactions that tell you how much actually is absorbed into other species. Yeah, for our particular stellar wind applications, to get an idea of how much of, well, how big this problem actually is, we have to care about 500 different species. So the I index ranges over like 500 indices. And we have about 5,000 reactions, which means that on the right-hand side, the non-zero case here will be have about like 5,000 of them, just to give you an idea of how big of a problem this actually is. Now, this equation looks quite difficult, so I'll try to simplify it a bit by only considering 1 and 2 body reactions. And then you can write it in this slightly more elegant form, where we have tensor A and a tensor B. And here we assume that there is a summation over all the repeated indices, right? So here we sum over the J index, and here we sum over the J and the K index. And then, yeah, so the idea of 500 species and 5,000 reactions translates into this as being a 500 dimensional problem. And there are 5,000 non-zero entries in the tensor A and B. So as such, this doesn't seem like too much of a problem, but the real problem arises when you realize that we have to do this for every point in our simulation, and that in, well, the simulation I just showed you before, we have about 1 million points. So we have to do this, but then also 1 million times, and that at every time step in our simulation. And that makes the whole problem prohibitively large in terms of the computational cost. So we, need to find some way out of here. And so the question we're going to ask ourselves is whether there is a way to approximate this entire chemical kinetics model. And in particular, we will ask ourselves whether we can map this model to a much simpler dynamical system. If you look into the literature, there's a whole bunch of literature with a whole bunch of different approaches that you can find. The first thing that was tried, actually also in our group, is to look at a reduced chemical network. So basically there you ask the question whether all the 5,000 reactions that we have are actually necessary and whether we can't get away by just using fewer reactions. It turns out that in particular cases, you can actually do that, but it's often a very risky business because you have to be very careful where you stay in your parameter space. And it's very difficult to predict a priori whether something is going to work or not. So that's, well, we've tried that, but it, turned out to be quite risky. Another approach is to work with these physics-informed neural networks or these neural operators just to speed up the computation of this set of ODEs. That all yield some interesting results, especially to get, well, some gets more precise result. It helps you get away with some of the numerical difficulties you usually have. But overall, by far, the biggest speed up that we have seen is by using these neural network surrogate models, where there's also been a whole bunch of research before, but I'm going to focus in particular on our most recent work that was presented by Silke Maas in her paper that was accepted last week, I think. Cool. So how does this, and the idea there basically is to build a surrogate chemical kinetics model. Now, what is the idea? So you remember the set of ODEs that we had to solve before. What we're going to do now is we're going to try to find a smaller set of coupled ODEs that acts on a much smaller space that we will call the latent space. And we will assume a particular form of this equation. As you can see, it looks very much like the previous equation, only we just added another constant term here, just because, then this would be, then this could be seen as an expansion in terms of in terms of set, right? And also because other people had very good results by just only considering this constant. So that's there are reasons why we actually added this constant here. So we have this other dynamical system, but now we will consider dimensions which are much smaller than what we originally had. So originally we had like a 500 dimensional system that we tried to solve, and now we try to map it to, well, something like 2, 4, 8, or 16 dimensional problem. So those are the different cases that we looked at. And well, because the dimension of the problem is way smaller, we can actually consider all entries of these tensors to be non-zero, just because, well, it doesn't really matter to make them sparse or not. There are not many entries anyway. Good. But then the question is, of course, how do we map our 500-dimensional dynamic system to this smaller reduced system? How do we map this to the latent space? Another question is, how do we then find the latent dynamics? So how do we find the corresponding coefficients C, A, and B that actually represent the chemical kinetics that we want to model? So to do the mapping to the latent space, we, well, don't use anything special. It's just an autoencoder where you just have two, an encoding and a decoding network. It's just 3 or 4 layers. It's actually quite small, and it works very nicely. And then how to find the latent dynamics? For that, we train the weights. Well, the weights are the coefficients of this tensor C, A, and B, together with the weights of this autoencoder. And we train this on a set of 30,000 chemical kinetics models that we just had laying around. So we had a bunch of models laying around for from a sensitivity analysis, and we just checked whether this might work. Okay, so yeah, here's just another schematic of how our surrogate model actually works. So as input, you give in the classical system, you would give your abundances of all your species at a certain time, and then out comes the set of abundances at some time delta t later. And for the surrogate model, you input your initial abundances into the encoder, which will map it to the latent space. Then there you evolve them by solving this reduced ODE system. For that, we use torch ODE because that allows us to then, at the same time, also train these coefficients. Well, it's a differentiable ODE solver, which then allows us to solve these, train also for these coefficients at the same time. So if we have this latent dynamics, this will give us the latent the point in the latent space at some time delta t, and then that can be decoded into the abundances at some later time delta t. Good. So that's the general idea of how we want to do this. The problem is if you use a naive implementation of this, so if you just use the thing I just described, it does not work and it fails dramatically. And that's also what everyone else. So I showed you this large list of previous work, and we discussed this with all of these people, and they kind of, well, everyone was very, very skeptical about this approach, and they all thought it wouldn't work. And indeed, they were right. It didn't work at first. But that was because we missed two crucial tricks to actually get it to work. The first thing is that we needed an empirical reparameterization of the latent dynamics. That's a whole bunch of fancy words, but what does it exactly mean? So so the problem is the following. If you just take a random ODE of this form, and so the coefficients of C, A, and B, you just, pull them randomly from some normal distribution, let's say between 0, with standard deviation 1 and with mean 0. So just some random values. And let's say we take some initial conditions, also random from a uniform distribution between -1 and 1. And let's then just look at how that would behave, what we would see if we would just solve for that dynamics. And what you would get then is the thing I show here below. So this is the evolution of this parameter z. Well, I subtracted z0 just to make it slightly nicer looking. And so that they all start from this nice point at 0. And then you can see the evolution of this, random system with random initial conditions. And what you see is that fairly quickly, the whole thing diverges. And fairly quickly, the whole thing, it kind of blows up and you get this quite erratic behavior. The problem is, if you're training such a system, once one of your elements in your latent space blows up and goes to infinity, it basically breaks your whole training process, your losses explode, and yeah, you're stuck and you can't train any further. And this happens all the time, so it's very inefficient to train to learn these coefficients and to learn the autoencoder in this way. So okay, that looked like, it's a very dramatic problem that we didn't really know how to solve. However, we realized that if you look at this plot, for every kind of set of initial conditions, so this, if you take everything between -1 and 1, and if you take these coefficients, if you assume them to be approximately normally distributed around 0 with a certain standard deviation, it's quite easy to predict how long this first region here will be. So for how long this dynamics actually will be quite regular, and you don't have these exploding variables. So you can quite easily predict this initial time step in which everything remains fine. So once we knew that, the idea that we had, or the trick that we wanted to apply, is that since we were only interested in applying our chemical kinetics model for a certain amount of time, we don't want to be able to evolve it all the way to infinity, because in our hydrodynamics, the hydrodynamical time step is finite, and it's usually relatively small. So we could actually adapt this or rescale this time step to be exactly within this regime where the dynamics of our latent system is actually very, very reasonable, and we are not plagued by these infinities further down. So that turns out to be a very useful way to get rid of these issues during training. Now I explain this as if this is a very evident thing. It wasn't at first, because when we first saw this, actually the first thing that we tried to do is looking at the ODE itself, because there is a whole bunch of literature about ODEs of this particular form and how you could solve them and how you could limit them. But yeah, in the end, it turned out that, well, you can apply as much theory as you want. In the end, the easiest thing to do is just empirically look at what the behavior is of this kind of system within a certain parameter range that you're interested in, and that you can control the system within your very specific parameter space. And that turned out to be a much quicker way to really get the system under control and make it do exactly what we wanted. So I think that was a very valuable lesson that we learned from this. Unfortunately, it didn't work immediately then, because there was a second ingredient that we missed, which was slightly more trivial, and that's the integrated loss. So when we were training these systems to really get them to get the surrogate model to really predict the dynamics well over the entire time step, we also needed to compute the loss or integrate the loss over the entire time step of the model. This kind of slowed training down a bit, but it turned out to be the key ingredient that we needed. And it's something that at first we hoped that if you just constrain it for smaller time steps, it will work, but it turned out you really need to, in your loss function, basically integrate over the entire time step. I think in the paper this makes slightly more sense. It's slightly more difficult to explain this just from that, but yeah, turned out to be a very important point in our training. And then combining those two tricks, it turned out that it worked fairly well. So here you can see, for example, so here I only show like a few of the chemical species. So these are just a small selection from the 500 species that we actually trained on. So you have CO, H2O, OH. And so on the horizontal axis, there is time. And on the vertical axis, there is the abundance, the relative abundance of all these species. And as you can see, the full lines are the original model, and the dotted lines are predictions. And yes, you can see they are all fairly consistent with each other. Actually, way more consistent than any of the previous work that we have seen. And also a big difference with us and previous work is that we can actually use a variable time step, because we solve the ODE within this latent space. We actually solve the ODE for a time step that is defined by the user. We have a much more flexible framework than anything that existed before. So we were extremely happy with this. All thanks to Silke Maas. So a well-deserved PhD for her. Of course, there are still a few open questions now. So first of all, how accurate do we need our surrogate model to be? Because as you can see, the lines don't overlap exactly, but we also know that there are large uncertainties on our original chemical kinetics model. So but to know how accurate we need to be, we actually also already need to know how accurate this original model is. And at the moment, we don't know that. So we need sensitivity analysis and an uncertainty quantification on the original model, which we are currently doing. So together with our collaborators, Marie van der Zande. Another thing that we desperately need is a benchmark for this kind of problems, because now we have a particular set of models in which we know that it works, but everyone in our field is kind of working on their own toy models. So I hope in September, there will be a workshop where we hopefully all come together and can agree upon a whole set of benchmark problems so that we actually can find out which models are performing best on these systems. So now I claim that we are currently the best model, but let's see until September whether that's actually the case. And then finally, there's of course a whole bunch of additional things we can do in our model. So we can add physics to the loss function. We can also encode more physics in the loss function. For instance, we tried things with mass conservation or element conservation. These are all symmetries or conservation laws that we know that should hold for the dynamical system that we are studying, but we're currently not using, mainly because it already works well enough for the type of applications that we're looking at. But yeah, so there is room for improvement, and we are aware of that. Good. So that was the one thing I wanted to talk about. So this surrogate model for chemical kinetics. Then the second thing I wanted to talk about is this problem of comparing our observations with simulations. And that it is very difficult because, yeah, you can start a simulation, but it's very difficult to hope that it will actually look like anything that we have observed before. Yes, so that's why we proposed this idea of reconstructing models based on our observations. But to, well, really appreciate how that works exactly, I think it's important that I first explain a bit what our observations actually are and what this data actually looks like. Because there is actually a lot of information encoded in these observations. Because a priori, I can imagine if you just see this 2D image, it might not be entirely clear how we can get a 3D model based on just this 2D image. You need some kind of depth information. And there's a whole dimension that we miss. But actually, we do have a lot of information along that third axis. But that third axis is not a spatial dimension, but that is the frequency in our case. Now I'm going to try to explain how this frequency information actually encodes also information along this spatial direction. But for that, I first need to explain what these images are, and this is typically what we call spectral line images. So let's see how I can break this down. So here you see this is a black and white version of the image that you saw before. And so what we see here is the CO emission. So CO is a molecule. You have two atoms close together, and as you can imagine, it's like two balls together. It rotates. It can fairly easily rotate. And these rotations of this molecule are quantized, right? So small that you can actually quantize the different rotation states. And it's fairly easily shifts between what we call the J=2 and J=1 rotation state. And when it switches from one rotation state to the other rotation state, it will emit or absorb energy in a very specific frequency. Because of quantum mechanics, the transition between these states is actually very narrowly fixed to a certain energy, and hence the corresponding relation has a very specific frequency. So if you would plot this radiation on a frequency axis, you would see it like this very peaked feature. And this is what we call a spectral line. That's why it's called spectral line emission or absorption, because it has such a peaked appearance in frequency space. Now, another important concept is that it's the concept of Doppler shifts. And Doppler shifts allow us to relate a frequency to a velocity. Because if the material is moving along the line of sight, the Doppler shift will shift the frequency to different, will shift the observed intensity. The observed radiation will be shifted to different frequencies depending on what the velocity is of the medium along the line of sight. So as such, each frequency, if you want, corresponds to a certain velocity channel. So then what we can do is we can look at different frequencies, and the images that we take at different frequencies then give us an idea of the material that is moving at different velocities along the line of sight. Yes, so and this gives you, so what you see here then is different images of the same object, but viewed from different frequencies around this certain central line. So what you see here is the material moving at different frequencies along the line of sight. And then you can imagine, well, if you know what material is moving at what velocity, if you then have some idea of the hydrodynamics that is going on, if you have some idea of this frequency field, you can actually derive where this emission is coming from along the line of sight, and in that way get get information about this depth direction that you actually miss in your 2D image. And that's exactly what we do, and that's exactly what we exploit in our model. I have some extra slides to show like how this, how we classically did this, because there has been a whole bunch of research to this, to do this in a classical way, but it's all very limited and all depends on a whole bunch of assumptions that you have to make on the velocity field. And we didn't want to do that. We wanted to do this in an as general way as possible without making too many assumptions. So how exactly can we now solve this inverse problem? First, we have to look at the forward problem, which we actually know quite well. And the forward problem is how, given a model, so given a 3D distribution of material, how can we then obtain the resulting images? So these resulting images of spectral lines. And for that, we have, well, typical, that's what we call radiative transfer solvers. That's, well, what I basically did in my PhD. I developed such a solver. So that's something that we're fairly confident in that we can do that. And then what we did now to make, well, to solve this inverse problem is we basically used a maximum a posteriori estimate for this model. And we tried to invert this forward solver in an inverse way. So how did we do that? Actually, we implemented our entire forward model for this in PyTorch. So we built a radiative transfer solver in PyTorch, such that, well, because of Autograd, we then had a easily differentiable forward model. And then we defined our model, so the density, the temperature, and the velocity, and all the variables that we needed. We defined them on these 3D tensors in PyTorch. And then simply by simply maximizing the a posteriori, the posterior distribution of this, we could get we could get an idea of the 3D models based on certain observations that we gave as an input. If you're familiar with inverse modeling, this might make some sense to you. However, you probably also know that it's very important when you're doing this. It's all very dependent on the particular kind of prior that you assume. In our case, so in this paper we explain this, we played around with a whole bunch of different physics modules. So in this case, our model is actually, so it gives you the density, the velocity, and the temperature in 3D of the model. And that's quite interesting because that's actually exactly what the input is of a typical hydrodynamics model. So what we did is we tried to use hydrodynamics as a prior on our model. Now it was a very fun exercise, and it actually allowed us to do some things, but yeah, unfortunately, it didn't seem like the hydrodynamics prior actually added much to our reconstructions. What did help in our reconstructions is all the typical smoothness priors that you can imagine. Smoothness priors, assumptions also on the symmetry. So if we penalized for deviations from spherical symmetry and things like that, those things seem to help a lot in our reconstructions. But yeah, all the fun things that we tried by using a lot of physics on our priors didn't really seem to help a lot. Although, yeah, we thought that we were putting a lot of physics in our problem, but it didn't really help. Nevertheless, this approach allowed us to make nice 3D models of actual observations, as the thing you can see here from Oracile. So the paper I quote here is the paper in which we present our methodology to do this. So this actual model is not in there yet, because I think we've spent a very long time to try to understand what is actually going on in here. So we're writing a separate paper on all the physics that is actually in this object, because there's actually a lot more to say about that other than just the method of reconstruction. So we probably have to wait 6 months to a year to get the whole explanation of all the astrophysics that is going on in this image. But I hope you can already see that just from a method point of view, it kind of works very nicely, and it can well, it allows us to get actual 3D models of observations that previously we had no idea how to interpret or how to play with. And now we can actually, well, they become tangible. We can look at them from different sides. We can now run chemistry models on them, and we're a lot more free in what we can actually do. All right. So I think that's everything I had to say. So thank you for your attention. Thank you for the invitation. Here are the two links to the papers again. If you have any questions, well, feel free to ask them now, or if you want to contact me later, here's my email address. I'm always very happy to talk about my work. Thank you very much.
Thank you, Frederik, for the nice talk. I think we can stop the recording. Is it, Marian?